Vibration-induced fatigue damage mechanisms is a part of mechanical and metallurgical failure mechanisms. Description of vibration-induced fatigue based on API 571, a form of mechanical fatigue in which cracks are produced as the result of dynamic loading due to vibration, water hammer, or unstable fluid flow. Vibration-induced fatigue damage is a type of material failure that occurs due to repeated cyclic stresses caused by vibrations. These vibrations can originate from various sources, such as machinery, vehicles, or even natural phenomena like wind or earthquakes. Unlike static loads, which exert a constant force, vibrations create fluctuating stresses, leading to a process of progressive, localized structural damage. This damage accumulates over time, eventually resulting in cracks and, ultimately, fracture, even if the stress levels are below the material's static strength. Here's a more detailed breakdown. Number 1 is about key characteristics, includes. The first of key characteristics is cyclic stress. The defining feature of vibration-induced fatigue is the repeated application of stress cycles. These cycles involve fluctuating between tensile and compressive stresses, or other stress states, around a mean stress value. The second of key characteristics is stress amplitude, the difference between the maximum and minimum stress in a cycle. Higher amplitudes generally lead to faster fatigue damage. The third of key characteristics is stress ratio, or R ratio, defined as the ratio of minimum stress to maximum stress in a cycle. It influences the fatigue life. For example, a fully reversed stress cycle, or R equals -1, has both tensile and compressive stresses of equal magnitude. The fourth of key characteristics is frequency, the rate at which the stress cycles occur. While not always a dominant factor, higher frequencies can sometimes accelerate fatigue damage due to the faster accumulation of damage. The fifth of key characteristics is stress concentration. Geometric discontinuities, e.g., holes, sharp corners, notches, act as stress concentrators. These areas experience significantly higher stresses than the surrounding material, making them prime locations for fatigue crack initiation. The sixth of key characteristics is damage accumulation. Fatigue damage is a cumulative process. Each stress cycle contributes a small amount of damage. The damage accumulates until a critical level is reached, leading to crack initiation and propagation. The seventh of key characteristics is crack initiation and propagation. Fatigue failure typically involves two main phases. Number 1 of main phases is crack initiation. Microscopic cracks begin to form at stress concentration points or material defects. This phase often takes up a significant portion of the fatigue life. Number 2 of main phases is crack propagation. The initiated cracks grow gradually under the cyclic stress. The crack growth rate accelerates as the crack lengthens, ultimately leading to complete fracture. Number 8 key characteristics is material properties. The fatigue life of a material is highly dependent on its properties, including. The number 1 of material properties is fatigue strength, the stress level below which a material can withstand an infinite number of stress cycles. The number 2 of material properties is endurance limit, the stress level below which a material is theoretically not prone to fatigue failure, only applicable for some materials, typically steels. The number 3 of material properties is tensile strength. Higher tensile strength generally correlates with higher fatigue strength, but this is not always a direct relationship. The number 4 of material properties is microstructure. The microstructure of the material, grain size, presence of inclusions, etc., significantly affects its fatigue resistance. And now let's continue to detail breakdown of how to describe vibration-induced fatigue. Number 2 is factors influencing vibration-induced fatigue. Number A of factors influencing vibration-induced fatigue is vibration amplitude. Higher vibration amplitudes result in higher stress ranges and faster fatigue damage. Number B of factors influencing vibration-induced fatigue is vibration frequency. The frequency of vibration can affect fatigue life, as higher frequencies could lead to more stress cycles per unit of time. Number C of factors influencing vibration-induced fatigue is mean stress. the average stress level in a cycle affects fatigue life, a higher mean stress generally reduces fatigue life. Number D, of factors influencing vibration-induced fatigue is material properties. The material's fatigue strength, tensile strength, and resistance to crack propagation all play a role. Number E, of factors influencing vibration-induced fatigue is environmental conditions, temperature, corrosion, and other environmental factors can significantly accelerate fatigue damage. Number F, of factors influencing vibration-induced fatigue is surface finish. Rough surfaces can act as stress concentrators, reducing fatigue life. Number G, of factors influencing vibration-induced fatigue is welding and joining techniques. Poorly designed or executed welds can introduce stress concentrations and reduce fatigue resistance. Number H, of factors influencing vibration-induced fatigue is design and geometry. Sharp corners, holes, and other features that cause stress concentrations are detrimental. Vibration-induced fatigue is a critical failure mode in engineering applications. Understanding the underlying principles, identifying potential sources of vibration, and implementing appropriate design and maintenance strategies are crucial for ensuring the reliability and longevity of structures and components. Vibration-induced fatigue affected material based on API 571, affected to all engineering material. Vibration-induced fatigue damage can affect a wide range of materials. The susceptibility to fatigue depends on the material's properties, the stress levels, the frequency of vibration, and the environment. Here's a breakdown of common materials and considerations. Number 1 is ferrous metals, steels. These are perhaps the most commonly affected due to their widespread use in structures, machinery, and transportation. Examples include: Number A, of ferrous metals is carbon steels, susceptible in a variety of applications. Number B, of ferrous metals is alloy steels, such as chromium, nickel, molybdenum steels, can offer improved fatigue resistance, but still susceptible. Number C, of ferrous metals is stainless steels, corrosion resistance is good, but fatigue can still be an issue, especially in harsh environments. Number D, of ferrous metals is cast irons, less fatigue resistance than wrought steels. Number 2 of common materials and considerations is non-ferrous metals, includes. Number A, of non-ferrous metals is steel. This is one of the most common materials used in construction, transportation, and manufacturing. It's susceptible to fatigue damage, particularly in bridges, aircraft components, and machinery. Different types of steel, e.g., carbon steel, alloy steel, stainless steel, have varying fatigue strengths. Number B, of non-ferrous metals is aluminum. Aluminum alloys are widely used in aerospace, aircraft, automotive, and packaging industries due to their lightweight and good strength-to-weight ratio. They are prone to fatigue, and their fatigue properties can be influenced by corrosion. Number C, of non-ferrous metals is titanium. Titanium alloys offer excellent strength, corrosion resistance, and high-temperature performance. They are often found in aerospace and biomedical applications. However, they are still susceptible to fatigue, especially under cyclic loading and in corrosive environments. Number D, of non-ferrous metals is copper and copper alloys, brass, bronze. These materials are used in electrical wiring, plumbing, and heat exchangers. Fatigue is a concern, especially in applications involving cyclic stress from vibration or temperature fluctuations. Number E, of non-ferrous metals is magnesium alloys, used in some automotive and aerospace applications due to their low density. They can be susceptible to fatigue. Number F, of non-ferrous metals is nickel alloys, used in high-temperature applications, can be susceptible to high-cycle fatigue. Number 3 of common materials and considerations is polymers, or plastics and rubbers, includes. Number A, of polymers is thermoplastics. These polymers, e.g., polyethylene, or PE, polypropylene, or PP, polyvinyl chloride, or PVC, nylon, or polyamide, polycarbonate, or PC, acrylonitrile butadiene styrene, or ABS, poly, methyl methacrylate, or PMMA, can experience fatigue failure under cyclic loading. Applications include pipes, housings, and automotive components. Number B of polymers is thermosets. These materials, such as resins such as epoxy, polyester, phenolic, are often used in composites. While generally stronger than thermoplastics, they can still fatigue. Number C of polymers is elastomers. Rubber materials are used in tires, vibration isolators, and seals. They are especially vulnerable to fatigue due to their viscoelastic behavior, time-dependent deformation. Number 4 of common materials and considerations is composites, includes. Number A of composites is fiber-reinforced polymers, or FRP, includes. The first of FRP is glass fiber-reinforced polymer, or GFRP. The second of FRP is carbon fiber-reinforced polymer, or CFRP. The third of FRP is aramid fiber-reinforced polymer, or AFRP. The fourth of FRP is fatigue resistance is a critical design consideration. Damage mechanisms include fiber breakage, matrix cracking, and delamination. These composites, such as carbon fiber reinforced polymers, glass fiber reinforced polymers, are increasingly used in aerospace, automotive, and wind turbine blades. Their fatigue behavior is complex and influenced by the fiber type, matrix material, fiber orientation, and manufacturing process. Delamination, separation of layers, is a common failure mode in composite fatigue. Number B of composites is metal matrix composites, or MMC. These combine a metal matrix, such as aluminum, titanium, with reinforcing fibers or particles. They can exhibit good fatigue resistance, but the interfaces between the matrix and reinforcement can be critical. Number 5 of common materials and considerations is ceramics, includes. Number A of ceramics is structural ceramics. These materials are known for their high compressive strength and high temperature resistance. However, they are brittle and relatively weak in tension, making them vulnerable to fatigue cracking. Number B of ceramics is glass. While glass can handle static loads, it is susceptible to fatigue failure under cyclic stress due to its brittle nature and the presence of surface flaws. Other materials which are common materials and considerations that affected causes by vibration-induced fatigue, includes. Number A of other materials is concrete, used extensively in construction. Fatigue is a significant concern, particularly in bridges and roadways exposed to repeated traffic loads. Number B of other materials is wood. Wood experiences fatigue under cyclic loading, and is less frequently utilized in applications subjected to sustained vibrational stress. Number C of other materials is electronic materials. Solder joints, printed circuit boards, and other electronic components can fail due to vibration-induced fatigue, particularly with thermal cycling. Factors affecting fatigue damage. Number 1 is stress amplitude. Higher stress amplitudes lead to shorter fatigue life. Number 2 is mean stress. The average stress level, mean stress, also influences fatigue life. Number 3 is frequency of vibration. Higher frequencies can accelerate fatigue, especially in materials with frequency-dependent properties, like elastomers. Number 4 is material properties. Strength, ductility, hardness, and microstructure all play a role. Number 5 is environment. Corrosive environments, temperature variations, and the presence of contaminants can accelerate fatigue damage. Number 6 is surface condition. Surface finish, roughness, scratches, and any surface treatments, such as coatings, shot peening, affect fatigue life. Number 7 is stress concentration. Geometric features such as holes, notches, and sharp corners can create stress concentrations that initiate fatigue cracks. Number 8 is loading type. Axial, bending, and torsional stresses have different effects on fatigue life. Almost all materials are susceptible to vibration-induced fatigue damage to some extent. The specific mechanisms of failure and the factors that influence fatigue life vary considerably depending on the material and the application. Understanding the potential for fatigue and designing components to mitigate its effects, such as, by reducing stress levels, improving surface finish, and using appropriate materials, is critical for ensuring structural integrity and preventing catastrophic failures. Vibration-induced fatigue critical factors based on API 571. The first is the amplitude and frequency of vibration as well as the fatigue resistance of the components are critical factors. The second is there is a high likelihood of cracking when the input load is synchronous or nearly synchronizes with the natural frequency of the component. The third is a lack of or excessive support or stiffening allows vibration and possible cracking problems that usually initiate at stress risers or notches. The critical factors of vibration-induced fatigue damage are multifaceted and can be categorized as follows. Number 1 is stress state, includes. Number A, of stress state is stress amplitude, the most significant factor. Higher stress amplitudes lead to faster fatigue crack initiation and propagation. The relationship between stress amplitude and fatigue life is typically depicted in an SN curve, stress versus number of cycles to failure. Number B, of stress state is mean stress. A non-zero mean stress can significantly influence fatigue life. Tensile mean stresses typically reduce fatigue life, while compressive mean stresses can sometimes increase it. Various correction factors, such as Goodman, Gerber, Soderberg, are used to account for mean stress effects. Number C, of stress state is stress concentration. Geometric features like holes, notches, and sharp corners create stress concentrations, amplifying the local stress. These regions are prime locations for crack initiation. The stress concentration factor, $K_T$, quantifies this amplification. Number D, of stress state is multiaxial stress. Real-world components often experience stresses in multiple directions. Fatigue damage under multiaxial loading can be more complex and may require special analysis methods, e.g., equivalent stress criteria like von Mises. Number E, of stress state is residual stress. Stresses induced during manufacturing processes, such as welding, shot peening, can either accelerate, tensile, or retard, compressive, fatigue crack initiation and propagation. Category 2 of critical factors can be considered by point of vibration characteristics views, includes. Number A, of vibration characteristics is frequency. The frequency of the vibration is important because it affects the number of cycles a component experiences over a given time. Very high frequency vibrations can lead to thermal effects due to internal friction which could further accelerate fatigue. Number B, of vibration characteristics is vibration mode shapes. The way a component vibrates, its mode shapes, determines the stress distribution. Components that bend/deflect experience the largest vibration-induced stress. Number C, of vibration characteristics is damping. Damping is the dissipation of energy from a vibrating system. Higher damping reduces the vibration amplitude and, consequently, the stress amplitude. Number D, of vibration characteristics is resonance. When the excitation frequency matches a natural frequency of the structure, resonance occurs, leading to significantly increased vibration amplitudes and potentially catastrophic fatigue failure. Number 3 of the critical factors of vibration-induced fatigue damage are multifaceted and can be categorized as material properties, includes. Number A, of material properties is fatigue strength, a fundamental material property, typically characterized by the endurance limit, for ferrous materials, or fatigue strength at a specific number of cycles. Higher fatigue strength generally means longer fatigue life. Number B, of material properties is tensile strength and yield strength. These properties provide an overall indication of the material's resistance to both static and cyclic loading. Number C, of material properties is ductility. Ductile materials can often accommodate stress concentrations better than brittle materials due to plastic deformation at crack tips. Number D, of material properties is microstructure. The the grain size, inclusions, and other microstructural features significantly impact fatigue resistance. Fine-grained materials generally exhibit better fatigue properties. Number E of material properties is surface finish. Surface roughness can introduce stress concentrations and accelerate crack initiation. Smoother surfaces generally improve fatigue life. Number F of material properties is material type. Different classes of materials, such as steels, aluminum alloys, polymers, have vastly different fatigue characteristics. Number G of material properties is temperature. Elevated temperatures often reduce fatigue strength, while cryogenic temperatures can sometimes improve it. Number 4 of the critical factors of vibration-induced fatigue damage are multifaceted and can be categorized as environmental conditions, includes. Number A of environmental conditions is corrosion. Corrosive environments, such as saltwater, chemicals, can significantly reduce fatigue life by promoting crack initiation and propagation, corrosion fatigue. Number B of environmental conditions is temperature. High temperatures can reduce material strength and accelerate fatigue. Number C of environmental conditions is humidity. High humidity can also promote corrosion and reduce fatigue life. Number D of environmental conditions is presence of other elements. The presence of other elements can impact the rate of fatigue. Number 5 of the critical factors of vibration-induced fatigue damage are multifaceted and can be categorized as component design and manufacturing, includes. Number A of component design and manufacturing is joints and connections. Welds, bolted joints, and other connections are often critical locations for fatigue failure. Number B of component design and manufacturing is manufacturing defects. Manufacturing processes can introduce defects, e.g., porosity in castings, cracks, machining marks, that act as stress concentrators and accelerate fatigue. Number C of component design and manufacturing is assembly processes. Improper assembly can introduce residual stresses that affect fatigue life. Other considerations. Number A is loading sequence. The order in which different stress levels are applied can influence fatigue life, especially in variable amplitude loading. Number B is crack growth rate. While not a primary factor in initiating fatigue, understanding the crack growth rate is essential for predicting the remaining fatigue life once a crack has initiated. Number C is inspection and maintenance. Regular inspections for cracks and timely maintenance are essential to prevent catastrophic fatigue failures. Number D is statistical variation. Fatigue life is inherently probabilistic. There is a significant amount of variation even under identical conditions. Accurate prediction and mitigation of vibration-induced fatigue damage require a comprehensive understanding of these interacting factors. A robust fatigue analysis typically considers stress analysis, vibration analysis, material properties, and environmental conditions. Experimental testing, especially fatigue testing, is often crucial for validating the models used in design. Vibration-induced fatigue damage mechanisms affected units or equipment based on API 571. The first is socket welds and small-bore piping at or near pumps and compressors that are not sufficiently gusseted. The second is small-bore bypass lines and flow loops around rotating and reciprocating equipment. The third is small branch connections with unsupported valves or controllers. The fourth is safety relief valves are subject to chatter, premature pop-off, fretting and failure to operate properly. The fifth is high-pressure drop control valves and steam-reducing stations. The sixth is heat exchanger tubes may be susceptible to vortex shedding. Vibration-induced fatigue damage can affect a wide range of units and equipment. Here's a breakdown by category. Number 1 is mechanical systems components, includes. Number A of mechanical systems components is engines and turbines, includes. The first of engines and turbines mechanical systems components is engine blocks, cylinder heads, crankshafts, connecting rods, pistons, valves, and other internal components. The second of engines and turbines mechanical systems components is turbine blades, discs, and casings in gas turbines and steam turbines. Number B of mechanical systems components is rotating machinery, includes. The first of rotating machinery of mechanical systems components is pumps, such as impellers, shafts, casings. The second of rotating machinery of mechanical systems components is fans, such as blades, hubs, shafts. The third of rotating machinery of mechanical systems components is compressors, such as impellers, rotors, stators. The fourth of rotating machinery of mechanical systems components is gearboxes, such as gears, shafts, housings. The fifth of rotating machinery of mechanical systems components is generators and motors, such as rotor/stator windings, bearings, shafts, frames. Number C of mechanical systems components is structures and frames, includes. The first of structures and frames in mechanical systems components is vehicular chassis, automobiles, trucks, trains, aircraft. The second of structures and frames in mechanical systems components is building frames and supporting structures, especially those near machinery or in seismic zones. The third of structures and frames in mechanical systems components is bridges and other infrastructure. The fourth of structures and frames in mechanical systems components is ship and marine structures. Number D of mechanical systems components is piping systems, includes. The first of mechanical systems components in piping systems is pipes, tubing, and their supports. The second of mechanical systems components in piping systems is welds and connections. The third of mechanical systems components in piping systems is valves and flanges. The fourth of mechanical systems components in piping systems is heat exchangers. Number E of mechanical systems components is fasteners and connections, includes. The first of mechanical systems components in fasteners and connections is bolts, screws, rivets, and other fasteners. The second of mechanical systems components in fasteners and connections is welds. The third of mechanical systems components in fasteners and connections is clamps and connectors. Number F of mechanical systems components is springs and dampers, includes. The first of mechanical systems components in springs and dampers is coil springs, leaf springs, torsion bars. The second of mechanical systems components in springs and dampers is shock absorbers and vibration dampers. Number 2 of a breakdown by category of vibration-induced fatigue damage can affect a wide range of units and equipment is electrical and electronic equipment, includes. Number A of electrical and electronic equipment is printed circuit boards, or PCBs, solder joints, traces, and components on PCBs, especially in harsh vibration environments, such as automotive, aerospace, industrial. Number B of electrical and electronic equipment is electronic components, capacitors, resistors, inductors, connectors, integrated circuits, ICs, especially leaded components. Number C of electrical and electronic equipment is wiring and cables, conductors and insulation, connectors and cable supports. Number D of electrical and electronic equipment is sensors and instrumentation, accelerometers, gyroscopes, pressure sensors, strain gauges, and other sensing devices. Number 3 of a breakdown by category of vibration-induced fatigue damage can affect a wide range of units and equipment is transportation systems, includes. Number A of transportation systems is aerospace, aircraft wings, fuselages, control surfaces, engines, and landing gear. Rockets and spacecraft structures and components. Number B of transportation systems is automotive, engine components, suspension systems, exhaust systems, body panels, and interior components. Number C of transportation systems is rail transportation, train car bodies, bogies, trucks, wheels, tracks, and signaling equipment. Number D of transportation systems is marine, ship hulls, propellers, engines, and onboard machinery. Number 4 of a breakdown by category of vibration-induced fatigue damage can affect a wide range of units and equipment is industrial and manufacturing equipment, include. Number A of industrial and manufacturing equipment is machine tools, spindles, slides, tables, and frames. Number B of industrial and manufacturing equipment is processing equipment, vibrating screens, conveyors, mixers, and crushers. Number C of industrial and manufacturing equipment is welding equipment, welding guns, cables, and associated equipment. Number D of industrial and manufacturing equipment is robotics, robot arms, joints, and end effectors. Number 5 of a breakdown by category of vibration-induced fatigue damage can affect a wide range of units and equipment is specific examples, includes. The first of specific examples is aircraft engines, turbine blades suffering from high cycle fatigue due to vibration from the engine's operation. The second of specific examples is automobile exhaust systems, cracking of exhaust manifolds or pipes due to engine vibrations and road-induced vibrations. The third of specific examples is offshore platforms, welding fatigue in structural joints of offshore oil and gas platforms due to wave-induced vibrations. The fourth of specific examples is wind turbines, gearbox failure due to vibrations from wind loads and rotor imbalances. The fifth of specific examples is hard drives, failure of components on hard drives within computers due to vibration from operation or external sources. The sixth of specific examples is electronic devices on spacecraft, components on PCBs are susceptible to damage from vibration during launch. Factors that influence vibration fatigue. Number 1 is vibration amplitude, the intensity of the vibration. Higher amplitudes generally lead to faster fatigue. Number 2 is frequency, the rate at which the vibration cycles occur. Resonant frequencies, where the equipment's natural frequency matches the excitation frequency, are particularly damaging. Number 3 is stress concentration, areas of high stress, such as sharp corners, holes, and notches, are prone to crack initiation and propagation. Number 4 is material properties, the material's fatigue strength, endurance limit, and ductility. Number 5 is mean stress, the average stress level during the vibration cycle. Higher mean stresses can accelerate fatigue. Number 6 is corrosion, the presence of corrosive environments can accelerate crack growth. Number 7 is temperature, high or fluctuating temperatures can affect material properties and fatigue life. Consequences of vibration-induced fatigue damage. Number 1 is cracking, the initiation and propagation of cracks in components. Number 2 is component failure, complete failure of a component, leading to equipment downtime and potential safety hazards. Number 3 is reduced performance, loss of equipment efficiency or accuracy. Number 4 is increased maintenance costs, frequent repairs and replacements. Number 5 is safety hazards, potential for catastrophic failures, leading to injuries or fatalities. Number 6 is unscheduled downtime, unexpected equipment failures disrupting operations. Appearance or morphology of vibration-induced fatigue damage mechanisms based on API 571. The first is damage is usually in the form of a crack initiating at a point of high stress or discontinuity such as a thread or weld joint, see Figure 4.57, vibration-induced fatigue of a 1-inch socket weld flange in a thermal relief system shortly after startup. And see Figure 4.58, cross-sectional view of the crack in the socket weld in Figure 4.57. The second is a potential warning sign of vibration damage to refractories is the visible damage resulting from the failure of the refractory and/or the anchoring system. High skin temperatures may result from refractory damage. Vibration-induced fatigue damage manifests in several characteristic ways, depending on the material, stress levels, and environmental conditions. Here's a breakdown of the typical appearances. Number 1 is crack initiation and propagation, includes. Number A, of crack initiation and propagation is initiation, fatigue cracks typically start at points of stress concentration. These could be: the first of crack initiation is surface imperfections, scratches, notches, machining marks, or corrosion pits. The second of crack initiation is microstructural features, grain boundaries, inclusions, or hard second-phase particles in the material. The third of crack initiation is geometric discontinuities, holes, fillets, or sharp corners. Number B of crack initiation and propagation is propagation. Once a crack initiates, it grows incrementally with each cycle of stress. The appearance of the crack surface reflects this stepwise progression. Key features include: the first of key features of propagation is beach marks, or striations. These are often visible on the fracture surface, especially with ductile materials. They are parallel lines or ridges, each representing the crack growth increment during a single stress cycle. The spacing between striations is related to the stress intensity factor range, delta K delta K delta K, and can indicate crack growth rate. Under an optical microscope, these may be difficult to see. The second of key features of propagation is macroscopic crack growth directions. The direction of crack propagation will often be roughly perpendicular to the applied tensile stress. This means that cracks often propagate in a plane perpendicular to the maximum tensile stress. The third of key features of propagation is crack surface roughness. Fatigue crack surfaces are usually rougher than those of a static overload fracture. Number 2 of a breakdown of the typical appearances of vibration-induced fatigue damage mechanisms is fracture surface features, includes. Number A of fracture surface features is fatigue zone. This is the region of the fracture surface where the crack grew due to cyclic loading. The first of fracture surface features of fatigue zone is flat, relatively smooth appearance in some areas, especially closer to the crack initiation site. The second of fracture surface features of fatigue zone is beach marks. The presence or absence, and clarity of beach marks depends on stress level, material, and environment. Number B of fracture surface features is final fracture zone, or overload zone. This is the area where the remaining material could no longer support the load and failed rapidly. The first of fracture surface features of final fracture zone often shows a more brittle fracture appearance with features characteristic of static or overload failure, such as dimples, in ductile materials cup and cone fracture, with numerous dimples indicative of microvoid coalescence. Cleavage facets, in brittle materials flat, shiny surfaces resulting from the transgranular fracture along crystallographic planes. The second of fracture surface features of final fracture zone is rougher and less predictable surface. Number 3 of a breakdown of the typical appearances is macroscopic observations, includes. Number A of macroscopic observations is crack location and orientation. Cracks often initiate at locations of high stress concentration and propagate in directions perpendicular to the tensile stress. Number B of macroscopic observations is crack length. The length of the fatigue crack will increase as the component experiences more cycles. The size of the fracture surface provides an indication of the severity of damage. Number C of macroscopic observations is component separation/failure. In the most extreme cases, the fatigue crack will propagate until the remaining cross-section is no longer able to bear the load. This results in complete failure, often with sudden and catastrophic consequences. Number D of macroscopic observations is material appearance. Changes in surface finish, such as discoloration due to oxidation or corrosion products formed within the crack, can be observed. Number 4 of a breakdown of the typical appearances is microscopic observations, includes. Number A of microscopic observations is slip bands and extrusions and intrusions. Microscopic examination of the material near the crack initiation site may reveal persistent slip bands. These bands are regions where plastic deformation is concentrated, contributing to crack initiation. At the surface, extrusions and intrusions, small steps in the surface, can sometimes be found. Number B of microscopic observations is transgranular versus intergranular fracture. Fatigue cracks can propagate through the grains of the material, transgranular, or along grain boundaries, intergranular, depending on the material properties and environment. Number 5 of a breakdown of the typical appearances is factors influencing appearance, includes. Number A of factors influencing appearance is material properties. Ductile materials tend to show beach marks and dimples, while brittle materials may exhibit cleavage facets. Number B of factors influencing appearance is stress amplitude and mean stress. Higher stress amplitudes and higher mean stresses generally lead to faster crack growth and different beach mark spacing. Number C of factors influencing appearance is loading frequency. Fatigue life can be affected by loading frequency. Number D of factors influencing appearance is environment. Corrosive environments can accelerate fatigue crack growth and change the appearance of the fracture surface. Number E of factors influencing appearance is temperature. Elevated or cryogenic temperatures influence material behavior and affect fatigue damage. Number F of factors influencing appearance is stress ratio. The ratio of the minimum to maximum stress in a cycle significantly influences fatigue life and the appearance of the damage. In summary, the appearance of vibration-induced fatigue damage includes crack initiation at stress concentrations, incremental crack propagation leading to beach marks, in some materials, a final overload fracture zone, and changes in the component's structural integrity. These observations help engineers determine the cause of failure, estimate the remaining life of components, and improve designs to mitigate fatigue failures. Prevention and mitigation for vibration-induced fatigue damage mechanisms based on API 571. The first is vibration-induced fatigue can be eliminated or reduced through design and the use of supports and vibration dampening equipment. Material upgrades are not usually a solution. The second is install gussets or stiffeners on small bore connections. Eliminate unnecessary connections and inspect field installations. The third is vortex shedding can be minimized at the outlet of control valves and safety valves through proper side branch sizing and flow stabilization techniques. The fourth is vibration effects may be shifted and a vibrating section is anchored. Special studies may be necessary before anchors or dampeners are provided, unless the vibration is eliminated by removing the source. Vibration-induced fatigue damage is a serious concern in many engineering applications, leading to component failure and potentially catastrophic consequences. Preventing or mitigating this damage requires a multifaceted approach. Here's a breakdown of prevention and mitigation strategies, categorized for clarity. Number 1 is design phase strategies. Prevention is key, includes. Number A of design phase strategies is avoid resonance, includes. The first of avoid resonance is frequency tuning, the most critical aspect. Design the structure so its natural frequencies are far from any anticipated excitation frequencies, sources of vibration. Calculate the natural frequencies using finite element analysis, FEA, or hand calculations based on the structure's geometry, material properties, and boundary conditions. The second of avoid resonance is vibration isolation. If resonance is unavoidable, use vibration isolators, e.g., springs, dampers, elastomeric mounts, to reduce the transmission of vibration from the source to the vulnerable component or structure. This reduces the amplitude of vibration seen by the susceptible part. Number B of design phase strategies is stress reduction, includes. The first of stress reduction is geometry optimization. Carefully design the geometry to minimize stress concentrations. Round sharp corners, use fillets, and avoid abrupt changes in cross-section. Finite element analysis, or FEA, is essential to identify and address areas of high stress. The second of stress reduction is material selection. Choose materials with high fatigue strength, endurance limit. Consider factors like yield strength. Materials with higher yield strengths generally have higher fatigue strengths. Ductility. Ductile materials can deform more before fracturing, which can be beneficial. Corrosion resistance. Corrosion significantly accelerates fatigue. The third of stress reduction is surface treatments, includes shot peening. introduces compressive residual stresses on the surface, which counteract tensile stresses caused by vibration. This significantly increases fatigue life. Surface hardening, e.g., case hardening, nitriding, increases surface hardness, making the component more resistant to crack initiation. Polishing reduces surface roughness, which can act as stress concentrators. The fourth of stress reduction is pre-stressing. Apply pre-stressing, such as, by tightening bolts to a specific torque, to components to create compressive stresses in areas susceptible to tensile stress from vibration. Number C of design phase strategies is connection and joint design, includes. The first of connection and joint design is robust joints. Joints are often weak points. Use robust joining methods. Welding, properly designed and executed, can provide strong, continuous joints. Bolting, select appropriate bolt sizes, grades, and tightening procedures, torque specifications. Preload bolts effectively. Riveting, another mechanically fastened method, but can lead to stress concentration around the rivet holes. The second of connection and joint design is minimize clearance/looseness, minimize any gaps or clearances in joints. Looseness allows for fretting and impact loading, which accelerates fatigue. The third of connection and joint design is avoid or minimize stress razors, design joints to avoid sharp corners, holes, or other features that can cause stress concentrations. Number D of design phase strategies is dynamic analysis, includes. The first of dynamic analysis is finite element analysis, or FEA, essential for a comprehensive understanding of the dynamic behavior of the structure. Perform modal analysis to determine natural frequencies and mode shapes. Perform forced vibration analysis to determine the response of the structure to specific excitation forces. Use FEA to identify high-stress regions and areas prone to fatigue. The second of dynamic analysis is modal testing. In many applications, physical modal testing can validate and refine the FEA results. Experimental modal analysis is also a useful technique to characterize the vibration response of the real structure. Number 2 of a breakdown of prevention and mitigation strategies is operational phase strategies. Mitigation and monitoring, includes. Number A of operational phase strategies, mitigation and monitoring, is control vibration sources, includes. The first of control vibration sources is equipment maintenance. Regular maintenance of vibration sources, e.g., rotating machinery, pumps, engines, is critical. Balance rotating components, lubricate moving parts, and replace worn components promptly. The second of control vibration sources is operational changes. If possible, reduce the intensity of the vibration source, change its operating speed, or operate it for shorter periods. Implement operating procedures that minimize the duration and severity of vibration. The third of control vibration sources is source isolation. Enclose vibrating machinery or components within vibration dampening structures. Number B of operational phase strategies of mitigation and monitoring is vibration monitoring and inspection, includes. The first of vibration monitoring and inspection is vibration sensors. Install vibration sensors, accelerometers, velocity sensors, displacement sensors, to monitor vibration levels in critical areas. The second of vibration monitoring and inspection is condition monitoring. Use the sensor data to monitor vibration trends and identify changes that could indicate damage. This includes techniques like trending analysis, track vibration amplitude over time. Increases in vibration levels often indicate impending failure. Spectrum analysis, or FFT, analyze the frequency content of the vibration. Changes in the frequency spectrum, such as the appearance of new peaks, can indicate specific problems, such as imbalance, misalignment, bearing wear. Envelope detection or demodulation. This technique is sensitive to rolling element bearing problems. Time domain analysis. Analyzing the signal directly in the time domain can reveal impacts and other faults. The third of vibration monitoring and inspection is regular inspections. conduct regular visual inspections for cracks, loose fasteners, and other signs of damage. Non-destructive testing, or NDT, methods can detect cracks before they propagate to critical lengths. Visual inspection, or VT, look for cracks, corrosion, and other visible damage. Dye penetrant testing, or PT, detects surface cracks. Magnetic particle inspection, or MT, detects surface and near-surface cracks in ferromagnetic materials. Ultrasonic testing, or UT, detects internal flaws. Eddy current testing, or ET, detects surface and near-surface flaws, and can be used to measure material properties. Number C of operational phase strategies of mitigation and monitoring is repair and retrofit, includes. The first of repair and retrofit is crack repair. If cracks are detected, repair them promptly. Welding, grinding, or other repair techniques may be used, but carefully considering stress concentrations and the long-term fatigue life of the repaired component. The second of repair and retrofit is component replacement. Replace damaged components before they fail catastrophically. Use the original design specifications, or consider upgrading to components with improved fatigue resistance. The third of repair and retrofit is retrofit vibration control. If vibration problems persist, consider retrofitting the structure with vibration isolation, damping treatments, or other vibration control measures. Number D of operational phase strategies of mitigation and monitoring is material and environmental considerations, includes. The first of material and environmental considerations is corrosion protection. Apply coatings, use corrosion-resistant materials, or implement other measures to protect the components from corrosion, which significantly accelerates fatigue crack initiation and propagation. The second of material and environmental considerations is temperature control. High temperatures can reduce material strength and accelerate fatigue. Control operating temperatures within design limits. The third of material and environmental considerations is load monitoring. Monitor the actual loads applied to the structure. Ensure that the load levels remain within the design envelope. Key principles and considerations in prevention and mitigation for vibration-induced failure damage mechanisms includes. Number 1 is early intervention. The best approach is to address vibration-induced fatigue during the design phase. Prevention is far more effective than mitigation. Number 2 is understanding the vibration environment. Thoroughly characterize the vibration environment. Identify the sources of vibration, their frequencies, amplitudes, and directions. Number 3 is fatigue life prediction. Use fatigue analysis techniques, such as SN curves, stress life, strain life, or fracture mechanics, to estimate the fatigue life of components. Number 4 is safety factors. Apply appropriate safety factors in design to account for uncertainties in loading, material properties, and environmental conditions. Number 5 is continuous improvement. Use data from monitoring and inspections to identify areas for improvement and refine the design or operating procedures. In summary, a comprehensive approach to preventing or mitigating vibration-induced fatigue damage involves a combination of careful design, robust construction, vibration control measures, continuous monitoring, and regular maintenance. This requires a multidisciplinary effort involving engineers, technicians, and other personnel with expertise in structural dynamics, materials science, and vibration analysis. Vibration-induced fatigue damage mechanisms inspection and monitoring based on API 571. The first is look for visible signs of vibration, pipe movement or water hammer. The second is check for the audible sounds of vibration emanating from piping components such as control valves and fittings. The third is conduct visual inspection during transient conditions, such as startups, shutdowns, upsets, etc., for intermittent vibrating conditions. The fourth is measure pipe vibrations using special monitoring equipment. The fifth is the use of surface inspection methods, such as PT, MT, can be effective in a focused plan. The sixth is check pipe supports and spring hangers on a regular schedule. The seventh is damage to insulation jacketing may indicate excessive vibration. This can result in wetting the insulation, which will cause corrosion. Vibration-induced fatigue damage is a serious concern in many engineering applications, and effective inspection and monitoring methods are crucial for detecting it early and preventing catastrophic failures. Here's a breakdown of the methods used. Number 1 is visual inspection, includes visual inspection description. The most basic method involves a thorough visual examination of the structure or component. Visual inspection techniques includes. The first of visual inspection techniques is surface crack detection, looking for visible cracks, especially in areas known for high stress concentrations, such as welds, corners, holes. The second of visual inspection techniques is paint cracking or flaking, can indicate surface stress and potential fatigue damage. The third of visual inspection techniques is deformations, observing for any unexpected bends, bulges, or distortions. The fourth of visual inspection techniques is corrosion. Corrosion can accelerate fatigue crack initiation and propagation. The advantages of visual inspection includes. The first of visual inspection advantages is simple, inexpensive, and readily available. The second of visual inspection advantages is can identify gross failures or advanced damage. Visual inspection limitations includes. The first of visual inspection limitations is only detects surface or near-surface damage. The second of visual inspection limitations is requires a trained inspector with experience. The third of visual inspection limitations is may not detect early-stage fatigue cracks. Number 2 of a breakdown of the methods used is non-destructive testing, or NDT, methods, includes. These methods allow for the examination of materials and components without causing damage. Several NDT techniques are commonly used for detecting fatigue damage. Number A of non-destructive testing, or NDT, methods is dye-penetrant testing, or PT. Dye-penetrant testing, or PT, description: a liquid dye is applied to the surface and penetrates into any surface-breaking cracks. The excess dye is removed, and a developer is applied, which draws the dye out of the cracks, making them visible. Dye-penetrant testing, or PT, advantages is simple, portable, and can detect very fine surface cracks. Dye-penetrant testing, or PT, is limitations is only detects surface-breaking cracks, requires a clean surface, and can be affected by surface coatings. Number B of non-destructive testing, or NDT, methods is magnetic particle testing, or MT. Description of magnetic particle testing, or MT, is a magnetic field is applied to the component, and ferromagnetic particles are applied to the surface. Cracks disrupt the magnetic field, causing the particles to accumulate at the crack location, making it visible. Advantages of magnetic particle testing, or MT, is detects surface and near-surface cracks in ferromagnetic materials. Relatively sensitive. Limitations of magnetic particle testing, or MT, is only applicable to ferromagnetic materials, requires surface preparation, and can be less sensitive than other methods for very small cracks. Number C of non-destructive testing, or NDT, methods is ultrasonic testing, or UT. Ultrasonic testing, or UT, description: high-frequency sound waves are transmitted into the material. Cracks or other discontinuities reflect the sound waves, and the reflected signal is analyzed to determine the location and size of the defect. Ultrasonic testing, or UT, techniques, includes. Pulse echo, measures the time it takes for a sound pulse to reflect back from a discontinuity. Through transmission, measures the loss of signal as the sound wave passes through the material. Advantages of ultrasonic testing, or UT, is, it can detect both surface and internal defects, provides information about the size and location of the defect, and can be used on a wide range of materials. Limitations of ultrasonic testing, or UT, is, requires skilled operators, can be more complex than other methods, and may require specialized equipment for certain geometries or materials. Number D of non-destructive testing, or NDT, methods is eddy current testing, or ET. Description of eddy current testing, or ET, is a coil is used to generate an alternating magnetic field in the component. Cracks or other discontinuities disrupt the eddy currents, which can be detected and measured. Advantages of eddy current testing, or ET, is rapid, sensitive to surface and near-surface cracks, can be used on conductive materials. Limitations of eddy current testing, or ET, is limited penetration depth, sensitive to surface conditions and material variations, and requires calibration. Number E of non-destructive testing, or NDT, methods is radiographic testing, or RT. Description of radiographic testing, or RT, is X-rays or gamma rays are passed through the component, and the resulting image reveals internal defects such as cracks, voids, and inclusions. Advantages of radiographic testing, or RT, is, it can detect internal defects, provides a permanent record of the inspection. Limitations of radiographic testing, or RT, is requires specialized equipment and safety precautions, can be expensive, and may not be suitable for all materials or geometries. Number F of non-destructive testing, or NDT, methods is acoustic emission testing, or AE. Description of acoustic emission testing, or AE, is, this technique monitors the sound waves, acoustic emissions, generated by the material during crack growth or other damage processes. Advantages of acoustic emission testing, or AE, is, it can detect damage in real time under load or during operation and can identify the location of crack initiation and growth. Limitations of acoustic emission testing, or AE, is complex signal analysis is required, the signal can be influenced by environmental noise, and the sensitivity can be affected by material properties and component geometry. Number 3 of a breakdown of the methods used is vibration monitoring, includes. Description of vibration monitoring is continuously or periodically measuring the vibration characteristics of a structure or component to detect changes that might indicate fatigue damage. Vibration monitoring techniques includes. The first of vibration monitoring techniques is vibration sensors, accelerometers, velocity transducers, displacement sensors mounted on the structure to measure vibration amplitude, frequency, and phase. The second of vibration monitoring techniques is data acquisition and analysis. The signals from the sensors are recorded and analyzed to identify any changes in the vibration signature. The third of vibration monitoring techniques is trend analysis, tracking changes in vibration characteristics over time to identify potential damage trends. The fourth of vibration monitoring techniques is modal analysis, determining the natural frequencies and mode shapes of the structure to identify changes in structural stiffness. Advantages of vibration monitoring includes. The first of vibration monitoring advantages is, it can detect early-stage fatigue damage by changes in vibration characteristics before visible cracks appear. The second of vibration monitoring advantages is, it can monitor the structure in real time, providing continuous or periodic health assessment. The third of vibration monitoring advantages is provides valuable information for condition-based maintenance. Limitations of vibration monitoring includes. Requires the installation of sensors and data acquisition systems. The interpretation of vibration data can be complex, requiring expertise. It can be sensitive to environmental noise and operational variations. Number 4 of a breakdown of the methods used is strain gauges, includes. Description of strain gauges is, strain gauges are sensors that measure the deformation, strain, of a material. They are often used to monitor the stress levels in a component. Strain gauges techniques includes. The first of strain gauges techniques is resistance strain gauges. Changes in resistance are proportional to the strain in the material. The second of strain gauges techniques is foil strain gauges. Thin metal foils are used to measure the strain. The third of strain gauges techniques is semiconductor strain gauges. Use semiconductor materials to provide higher sensitivity. Advantages of strain gauges includes. The first of advantages of strain gauges is provide direct measurements of strain and stress. The second of advantages of strain gauges is can be used to monitor stress concentrations in critical areas. The third of advantages of strain gauges is useful for fatigue life assessment. Limitations of strain gauges includes. The first of limitations of strain gauges is point measurements may not capture the overall stress distribution. The second of limitations of strain gauges is requires careful installation and calibration. The third of limitations of strain gauges is can be sensitive to temperature and other environmental factors. Number 5 of a breakdown of the methods used is infrared thermography, includes. Description of infrared thermography is uses infrared cameras to detect temperature variations on the surface of a component. Fatigue damage can cause localized heating due to friction or energy dissipation. Infrared thermography techniques includes. The first infrared thermography techniques is passive thermography, measures the natural heat emitted by the component. The second infrared thermography techniques is active thermography, applying external heat sources to the component and observing the thermal response. Advantages of infrared thermography includes. The first of advantages of infrared thermography is non-contact inspection. The second of advantages of infrared thermography is can detect changes in temperature, suggesting damage or stress. The third of advantages of infrared thermography is, it can identify areas with high friction or heat generation. The limitations of infrared thermography includes. The first limitations of infrared thermography is may require a temperature gradient for effective damage detection. The second limitations of infrared thermography is affected by ambient temperature and emissivity of the surface. Number 6 of a breakdown of the methods used is fracture mechanics and fatigue life assessment, includes. Description fracture mechanics and fatigue life assessment is employing theoretical models and analysis techniques to predict fatigue life and assess the damage tolerance of a component. Fracture mechanics and fatigue life assessment techniques includes. The first fracture mechanics and fatigue life assessment techniques is stress life, or SN, curves, relate stress amplitude to the number of cycles to failure. The second fracture mechanics and fatigue life assessment techniques is strain life, εn, curves, used for low cycle fatigue. The third fracture mechanics and fatigue life assessment techniques is for fracture mechanics, using principles to predict crack growth rates. The fourth of fracture mechanics and fatigue life assessment techniques is finite element analysis, or FEA, simulating the stress distribution and dynamic response of the structure to identify areas prone to fatigue. The advantages fracture mechanics and fatigue life assessment includes. The first of the advantages of fracture mechanics and fatigue life assessment is it can provide a quantitative assessment of fatigue life and remaining useful life. The second of the advantages of fracture mechanics and fatigue life assessment is it can helpful in predicting the effects of vibration on fatigue life. The third of the advantages of fracture mechanics and fatigue life assessment is it used to develop inspection schedules and maintenance plans. The limitations of fracture mechanics and fatigue life assessment includes. The first of the limitations of fracture mechanics and fatigue life assessment is, it relies on accurate material properties, loading conditions, and environmental factors. The second of the limitations of fracture mechanics and fatigue life assessment is, it is simplified models may not accurately capture all the complexities of fatigue behavior. Number 7 of a breakdown of the methods used is advanced techniques, or less commonly used, includes. Number A, of advanced techniques, or less commonly used, is digital image correlation, or DIC, uses digital images to track surface deformations and identify areas of high strain concentration. Number B, of advanced techniques, or less commonly used, is X-ray diffraction, can be used to analyze the residual stress distribution in the material, which can be an indicator of fatigue damage. Number C, of advanced techniques, or less commonly used, is neutron diffraction, similar to X-ray diffraction, but uses neutrons to penetrate deeper into the material. The selection of appropriate inspection and monitoring methods depends on: Number 1 is criticality of the component. Higher criticality requires more frequent and sensitive inspections. Number 2 is operating environment. The vibration environment, temperature, and corrosive conditions will influence method selection. Number 3 is material. Different materials respond differently to fatigue. Number 4 is budget and resources. Cost-effectiveness is a key factor. Number 5 is accessibility, the ability to access and inspect the component. Number 6 is stage of damage expected. Choose methods that will be effective in the early stages of damage. Often, a combination of methods is used to provide the most comprehensive assessment of vibration-induced fatigue damage. For example, a combination of visual inspection, vibration monitoring, and NDT methods may be used to monitor the health of a rotating machine. The chosen method should be appropriate for the application and the potential failure modes. Thank you.